is an international scientific organization. This organization strives to advance chemistry, in part by setting global standards for names, symbols, and units. It is important because it ensures that a spoken or written chemical name leaves no ambiguity concerning which chemical compound the name refers to. Each chemical name should refer to a single substance. A less important aim is to ensure that each substance has a single name.
Hydrocarbons are compounds containing only hydrogen and carbon. These are widely occur in nature, such as in petroleum, in gas, and in coal. Hydrocarbons can be considered as parent organic compounds from which other classes of compounds are derived by replacing one or more hydrogen atoms by the atoms of the other elements or groups. And now, hydrocarbons can be classified in two classifications, which are the acyclic hydrocarbons and the cyclic hydrocarbons. The first one, which are the acyclic hydrocarbons, they are compounds of carbon and hydrogen in which the carbon atoms are linked in such a manner that they do not form a cyclic system. And the second classification, which is the opposite, is the cyclic carbons, which they do form a cyclic system.
Okay, so we're gonna learn how to name alkanes. Alkanes are hydrocarbons bonded by single bonds between carbon atoms. And in order to name them, we have to follow these 5 steps right here. But so we get a better idea, we're going to test them on this example right here. So the first thing we have to do is count the number of carbons in the longest carbon chain. First, we need to take a look at our possibilities that are, first of all, 1, 2, 3, 4, 5, 6, 7, and 8 carbons long. Our second possibility that is 1, 2, and 3 carbons long. Our third possibility that is 1, 2, 3, 4, and 5 carbons long. And our last possibility that is 1, 2, 3, 4, 5, 6, 7, 8, and 9 carbons long. So this is an easy decision to make because 9 is bigger than 8, 5, and 3. So we're gonna circle it so we can identify it more easily. Right, so the second step says that we have to number each carbon, giving all the substituents the lowest numbers. What does this mean? That we have to give each carbon in the longest carbon chain a number. But how are we gonna do that? Is this one going to be carbon number 1, or is this one right here going to be carbon number 1? In order to decide this, we have to take a look at our substituents. For example, if this were carbon number 1, it will be carbon number 1, carbon number 2, and carbon number 3. And the substituent will be positioned on carbon number 3. But what if we start over here? This will be carbon number 1, this will be carbon number 2, and the substituent will be positioned on carbon number 2. So, our lowest number, of course, is 2 rather than 3. So we have to start from our right side. That is, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Once we've done this, we have to name our alkane. So we have 3 substituents right here, and we're gonna name it trimethyl because of the prefix. And we write first trimethyl, and then we have to locate our substituents. Like this one is located on carbon number 2, carbon number 4, and carbon number 7. So we're gonna order them like this: number 2, comma number 4, comma number 7, and a hyphen to separate numbers from words. And then we're gonna use the prefix known for 9 and add "ane" in the end because we're dealing with an alkane.
Alkenes.
are unsaturated hydrocarbons that contains at least one carbon-carbon double bond. Here we have an example. Is this one, CH2, CH3, an H, another H, and another H. How can we name it? Well, first we have to find the longest continuous chain of carbon atoms that include the double bond. Here, our longest chain will be this one because it has 4 carbon atoms. We don't have any other chain that has a lot of carbon atoms. Then we have to numbering them from the left side to the given double bond to the lowest number designation. The parent alkane name is butane. We start to name it, and this is the 1, the 2, the 3, and the 4. Well, the step number 3 was to number the chain starting from the end closest to the double bond and give the double bond the lower number of its double bonded carbon atoms. 4. A compound with 2 double bonds is a diene. A triene has 3 double bonds and a tetraiene has 4 double bonds. The numbers are used to specify the location of the double bonds. Well, how can we name this compound? First, we have the double bond in the second position. It is going to bind the first carbon to the second carbon. Therefore, the name of the compound is but1-ene. Why? Because it is bonded the first and the second, so it is the first bonding, so it is going to be but of, that means 2, 1, the first bonding, and ene because it is an alkene. But the old IUPAC name is this one, 1-butene. Putting the designation within the name eliminates any confusion.
Now we're gonna learn how to name alkynes. Alkynes are hydrocarbons bonded by triple bonds between carbon atoms. And the steps we have to follow are the same we used when naming alkenes. So the first thing we have to do is identify the carbons we have in our formula and identify the longest chain. So we have 1, 2, 3, 4, 5 carbons. And because this is our longest and only chain, we're going to work with that. So we have the first part of our name, that is pentyne, because we're dealing with number 5. And then we have to continue numbering the carbons. And we have to ask ourselves the same question. Is this going to be carbon number 1 or is this going to be carbon number 1? If we number from here, it will be number 1, number 2, and number 3. And our triple bond will be starting on carbon number 3. But because we want to give them the lowest number, we have to start from the right side. So it will look a little bit like this. It will be 1, 2, 3, 4, and 5. And now that we have them numbered, we use our number 2 to finish our name. And we add 2-pentyne.
The aromatic or arenes. Naming these aromatic compounds isn't quite so straightforward as naming chain compounds. Often, more than one name is acceptable, and it's not uncommon to find the old names still in use as well. First, we have to start with the benzene ring. All aromatic compounds are based on benzene, C6H6, which has a ring of 6 carbon atoms and has this symbol, that is an hexagon with a circle inside. Each corner of the hexagon has a carbon atom with a hydrogen attached. An example is this one. We have to draw the hexagon with the circle. Then we have this chlorine atom. Well, this simplified formula is C6H5 chlorine. The name is chlorobenzene. Why? Because these cases, when there is only one group attached to the benzene ring, they are based on benzene. Well, what do we have now? We call it as this: phenyl chloride. Why? Because whenever you draw a benzene ring with one of the other thing attached to it, you are in fact drawing a phenyl group. In order to attach something else, you have to remove one of the existing hydrogen atoms, and so automatically make a phenyl group. By the way, aromatic compounds are characterized by the presence of one or more rings and are uniquely stable structures, a result of strong bonding arrangements between certain p electrons of molecules. Benzene, which serves as the parent compound of numerous other aromatic compounds, such as toluene and naphthalene, contains 6 planar p electrons that are shared among the 6 carbon atoms of the ring. Here we have another example. We draw the hexagon through this, and we start writing the hydrogens. This is one bonding, one bond on the hydrogen. And how do we call this? We have 6 carbons and 6 hydrogens. This is called as benzene. But why do we have 6 carbon atoms? Because, as you may know, each ring has 6 carbon atoms, that are these ones: 1, 2, 3, 4, 5, and 6. When there are multiple substituents, ring atoms are numbered to minimize the number assigned to the substitute positions. The substituted benzene rings can be named based on the relative positions of the substituents. The prefix ortho. It is used if the substituents occupied adjacent positions of the ring 1 through meta. It is used if the substituents are separated by 1 ring positions 1 and 3, and para if they are found on opposite sides of the ring 1 and 4. So we are going to write this: ortho 1 and 2, meta 1 and 3, and para 1 and 4.